My name's Chase Vallin.
I'm Taylor Patterson.
Cary Hendrix.
Zackery Vallin's videoing.
For our project, we were tasked with building a Stirling engine. This is the one we built. These two we got from Professor Sisk and Cooley. They're three different styles. Ours is an alpha style, and the basic concept behind them all is that they're a heat engine. They have a heat source and a hot side and a cold side. And in this one, it's a cup of water, and that's what's heating the bottom plate of this to make it run. And you have to spin it a certain way to get it running. The cold side is just the air in the room. For this one, it's a little different. It's got heat fins here, and alcohol is our heat source, like a candle. And it's heating up this cylinder, or this side of it. And this is the cold side for the atmosphere. And it's just compressing, heating up the air and compressing it, and then the cold side cooling down. And that's what keeps the heat engine going on all these. And on ours we have the cold side, which is the ice, and then we're gonna move this over for the heat side in a second. And we also want to show you the thermal imaging of it to show you the difference between the hot side and the cold side, for an example. And on this one, you can see in the camera that the hot side is obviously a different color, it's red. And on this side, it's a cooler temperature, and that's the transfer of the air temperatures going through there. And on this one, the coffee cup, you can see up the coffee cup's a lot redder, or hotter, which is red. And the top's the atmospheric air, which is the cool, or the sink side.
Okay, this is our alpha style Stirling engine. We got these glass tubes and polished the insides of them. And then we 3D printed this wheel and put some nuts in it to give it some weight and more momentum. And we 3D printed these little brackets as well. And then we've got this tubing to let the heat transfer. And the heat is the hot side, this is the cold side. If you look in the thermal imaging camera, this side should be white or red, and this side's probably black because it's cold.
And the Stirling engine, obviously the main problem is friction, so you want to minimize that as much as you possibly can. And maybe with plastic on metal, that's not the best idea. And for our heat sink, we used plastic, and once we had this going and it got so hot, it actually melted these brackets, which wasn't a very good design on our end, but it had it for a moment. And that's why we have the ice as a cold sink to cool it down and keep the two different temperature differences. And our 3D printing, the wheel, the momentum is supposed to keep it going, to keep the inertia going. And for our math on the efficiency side of it, we got the heat source to be around 300 degrees Fahrenheit, and our cold side is around 35 degrees Fahrenheit. And this is our sink, that's our source side. And to calculate some numbers to it, from the candle here, the alcohol that you can see, puts out 100 BTUs per hour, which is 1.67 BTUs per minute, which is the Q dot hot side. And once we compared the hot and cold to get the most or maximum efficient this heat engine could ever be, we came out with 35.26% efficiency for our setup that we have here. And to get the work output out, we took our efficiency times our Q dot hot side or whatever, and we got 0.1 or 0.59 BTUs per minute, which was our power output of our engine. And for our Stirling engine, obviously, once again, friction was probably the biggest issue here. And after polishing the syringes and glass tubes, it helped a little bit, but it still didn't seem to, still had friction problems in it.